Traditional 22K gold jewelry manufacturing in Sri Lanka is an age-old craft that combines centuries-old techniques with modern methods. During a visit to a jewelry manufacturing hub on C Street, a renowned area for jewelry production and retail, the intricate process of creating 22K gold jewelry was observed in detail. This area, packed with numerous small workshops, highlights the enduring heritage of handcrafted jewelry production. The workshops were compact, bustling with skilled jewelers seated closely together, working tirelessly with hand tools. The artisans employed manual fabrication techniques that have been passed down through generations, including hammering and forming gold. The atmosphere inside the workshop was intense due to the combined heat from the Sri Lankan climate and the furnaces used for melting and annealing gold. One fascinating aspect of the process was the use of charcoal furnaces combined with hand-powered air blowers to heat gold. These traditional methods were employed alongside modern electric furnaces, showcasing a seamless blend of old and new techniques. Watching molten gold being poured into molds and then annealed was an incredible experience, emphasizing the skill and precision required for this craft. Polishing the gold to give it a finished shine involved various tools, including lighters and jeweler torches, demonstrating the resourcefulness of the artisans. The jewelers showcased remarkable speed and dexterity, especially while forming links for gold chains. Using hammers and pliers, they annealed and assembled the links, demonstrating their mastery over the craft. Another traditional technique observed was piercing and sawing, fundamental processes in hand-fabricated jewelry. These methods allowed artisans to create intricate patterns and designs with great precision. Despite the availability of modern tools, many craftsmen still preferred using hand-blown torches for soldering. The level of control they exhibited with these tools was astounding, reflecting years of practice and dedication. The working environment was notably warm, prompting many jewelers to work shirtless for comfort. They sat on the floor, often cross-legged, focusing intently on their tasks. Krastsvetmet is a renowned manufacturer specializing in high-quality machine-woven chains and bracelets crafted from premium materials, including 585 and 750 gold alloys, 950 platinum, 850 palladium, and 925 silver. The company offers a diverse range of jewelry products, featuring 30 base chain designs that are developed into an impressive collection of 180 types of chains and bracelets. This extensive variety demonstrates Krastsvetmet's dedication to meeting diverse customer preferences and market demands. A significant focus of Krastsvetmet's jewelry production is the manufacturing of hollow chains. The company currently produces 18 distinct types of hollow chains, as well as a series of diamond-cut gold bracelets. These products highlight the company's expertise in precision craftsmanship and advanced jewelry-making technologies. The production process at Krastsvetmet follows a full manufacturing cycle, starting with alloy casting and progressing through various stages, including diamond cutting and finishing. This comprehensive approach ensures high-quality output and consistency across all products. By managing every step of production in-house, Krastsvetmet maintains strict quality control and leverages efficient manufacturing techniques. Krastsvetmet's journey into jewelry production began in 1991 with the decision to diversify its offerings. Actual production commenced in 1994, initially focusing on 925 silver jewelry. Building on this foundation, the company expanded its product line to include gold and platinum pieces by 1996. This strategic progression reflects Krastsvetmet's ability to innovate and adapt to evolving market trends. Fire assay, an ancient yet highly precise technique, has stood the test of time as the gold standard for extracting and analyzing precious metals. This method, rooted in tradition and perfected through centuries, remains indispensable in modern mineral processing due to its unmatched accuracy. The process begins with sample preparation, where a representative portion of the ore, concentrate, or bullion is finely ground to ensure homogeneity. This step is critical as it exposes precious metals for subsequent analysis and guarantees the sample reflects the composition of the entire batch. Next is the fusion process, where the prepared sample is mixed with a flux, a blend of lead oxide, litharge, and a reducing agent such as borax or soda ash. This mixture facilitates the separation of metals from impurities. Heated in a crucible at temperatures between 1000 degrees Celsius and 1200 degrees Celsius, the flux reacts with unwanted materials, forming a slag that separates from the molten metal. Following fusion, the molten metal undergoes cupellation, a refining step that isolates precious metals. The molten mixture is poured into a porous cupel made of bone ash or similar absorbent material, and heated in a controlled, oxygen-rich atmosphere. Base metals oxidize and are absorbed into the cupel, leaving behind a bead or prill of precious metals, including gold, silver, and platinum group metals, PGMs. To further purify the prill, parting is performed when gold and silver are both present. This involves treating the bead with nitric acid to dissolve silver, leaving pure gold behind. The dissolved silver is precipitated using a reducing agent such as copper, forming silver chloride for collection and weighing. Finally, the prill undergoes weighing and analysis using a precision balance. Combined with data on flux weight and other parameters, the precious metal content in the original sample is accurately calculated. The process begins with extracting a small sample from unrefined gold, referred to as doré or scrap. This sample undergoes a preliminary analysis using an XRF machine, which determines its composition. Based on the analysis, calculations for partitioning are carried out, and the sample is weighed using a highly sensitive analytical balance. The weighed sample is wrapped in lead foil and placed into preheated porous containers called cupels. These cupels are heated in a cupellation furnace set to the desired temperature. During this stage, the base metals in the sample oxidize, leaving behind the precious metals. After cooling, the resulting precious metal beads are separated and manually cleaned. The beads are then annealed and shaped into cornets through hammering or pressing. These cornets contain silver, which must be eliminated through a process called parting. The cornets are washed twice with concentrated nitric acid, which dissolves the silver without affecting the gold. Following the removal of silver, the gold cornets are dried, cooled, and annealed again to make them cohesive, homogeneous, and rigid. A final weighing determines the purity of the gold, completing the fire assay process. Guyana's gold mining sector contributes significantly to its economy and supports over 15,000 artisanal and small-scale miners. Despite this, gold mining remains a driver of deforestation. However, with deforestation rates below 0.05%, Guyana represents a beacon of hope for sustainable mining practices amid the global environmental crisis. Conservation International Guyana, in collaboration with partners, is implementing responsible mining initiatives, like the Planet Gold Guyana project to reduce mercury usage and protect forests. The gold kacha is a gold concentrator designed to process 1 to 3 tons of material per hour, even capturing fine particles as small as powdered gold. Made from rust-resistant polyplastic, it is easy to set up and requires a 220-volt power connection and a water source. Its barrel-shaped design contains shelves, called riffles, which trap gold particles during operation. Continuous water flow aids in concentrating gold, and the collected material can be washed out efficiently for further processing. The gold cube is another concentrator that processes 100 kilograms of concentrate per hour, best suited for particles under 3 millimeters. Equipped with a 12-volt water pump, it uses shelves with matting to trap heavier particles, including gold. The first shelf, called the slick plate, evenly distributes material, while subsequent shelves create a whirlpool effect to separate gold from lighter particles. This compact design improves gold recovery rates while minimizing operating costs. The Blue Bowl is a lightweight and portable concentrator, ideal for processing up to 1 kilogram of material per hour. It requires a stable, leveled surface and uses a water pump to create a swirling effect that separates gold from lighter materials. Its high efficiency makes it suitable for refining concentrates obtained from the gold kacha or gold cube. Gold particles settle at the bottom, while lighter materials are flushed out through the bowl's center hole. These technologies can be used individually or in combination to create an efficient mercury-free gold recovery process.
Gold is made in Kirkland Lake, a mining town in northeastern Ontario, Canada. The area is known for its rich gold deposits, with over 30 mines producing more than 47 million ounces of gold. Currently, there is one operating mine called Macassa, run by Kirkland Lake Gold, which has poured 5 million ounces of gold. However, extracting the gold is a challenging task due to the over 5,000 feet of solid rock that separates the surface from the gold deposits. Miners descend over 4,500 feet underground to reach the gold deposits. They travel through drifts, which are large tunnels, to reach their work sites. Geologists collect rock samples by drilling deep into the rock using diamond drills. These core samples are examined to determine the direction for further drilling. Engineers then plan a specific drilling pattern, and the miners drill holes in the face of the drift accordingly. These holes are loaded with explosives. Once everyone is safely back on the surface and the tunnels are clear, a controlled blast occurs, extending the tunnel by about 10 feet. The muckers, who are responsible for removing the debris from the blast, come in and clear the area. Some of the muck removal processes are even controlled remotely from the surface. The muck, or broken rock, is then separated, and the ore containing the gold is identified. After the muckers have cleaned up the area, miners reinforce the tunnel with screens and rock bolts using tools such as the jackleg drill and stoppers. The ore is transferred from the muck area to the ore passes, where trucks are loaded from chutes. The muck is then hauled to the ore pass rock breaker, which processes the muck into 16-inch squares. The ore is sent to the ore pass and loaded into a skip at the loading pocket. From there, the ore is transported to the surface via the shaft. It's interesting to note that Clayle Gold's Macassar mine was the first company in Canada to use battery-powered trucks, reducing emissions, and taking up a smaller footprint compared to diesel trucks. The batteries of these trucks are charged in an underground charging station. Once the ore reaches the surface, it is crushed into pieces about 4 inches in diameter using a jaw crusher. The crushed ore then travels on conveyor belts to other crushers that further reduce its size. The final crusher reduces the ore to a size of 7/16 of an inch, similar to a Cheerio. From there, the ore is sent to the mill via a conveyor belt and dumped into the fine ore bin, which can hold 1,600 tons of ore. The ore is fed into a grinding mill, which contains steel balls that grind the ore to make it smaller. After grinding, the ore goes through another grinding mill with smaller balls to further dry it into a finer slurry. A cyclone separates the larger pieces from the finer pieces, and the finely ground ore, similar to flour, is then transferred to leach tanks. In the leach tanks, the ore is mixed with chemicals that extract the gold from the ore. Once the gold is removed, it is heated and mixed with chemicals to purify it. The purified gold is then dried in an oven overnight. By morning, the gold takes on an ash-like appearance. To further process the gold, it is mixed with chemicals and poured into a furnace heated to over 1000 degrees Celsius. The gold becomes molten and separates into matte and slag. The slag, which contains waste materials, is poured out first as it floats on top due to the gold's heaviness. The remaining molten gold is poured into molds to form bars. After the molten gold is poured into molds to form bars, a sample is extracted to determine the gold and silver content. This sample is carefully taken and analyzed to assess the purity of the gold. Typically, the gold content in the bars ranges from 80 to 90%, indicating a high concentration of pure gold. Additionally, the sample is also examined for its silver content, which usually falls between 6 to 12%. These precise measurements help ensure the quality and value of the gold bars before they are cooled, weighed, stamped, packaged, and sent to a refinery for further processing. The smelting process of aluminum begins with bauxite, which is the natural ore used to make aluminum. Bauxite is a reddish-brown rock that is primarily composed of aluminum hydroxide minerals, along with various impurities such as iron oxides, silica, and titania. To extract aluminum from bauxite, it undergoes a series of refining steps. The first step in the smelting process is the crushing and grinding of bauxite into a fine powder. This process aims to increase the surface area of the bauxite particles, allowing for more efficient chemical reactions during the subsequent refining stages. The crushed bauxite is then refined into alumina through the Bayer process, named after its inventor, Carl Bayer. The Bayer process involves the digestion of bauxite in a caustic soda solution at high temperatures and pressures. This dissolves the aluminum hydroxide minerals present in bauxite, while leaving behind the impurities. The resulting solution, called sodium aluminate, is then clarified, and any remaining impurities are removed. Next, the sodium aluminate solution undergoes precipitation, where aluminum hydroxide is separated from the solution by controlling the temperature and adding seed crystals. The precipitated aluminum hydroxide is then calcined or heated to remove water and transform it into aluminum oxide. The alumina obtained from the Bayer process is a white powder that serves as one of the main raw materials for aluminum smelting. It is a highly stable compound with a high melting point, making it suitable for the subsequent reduction process. The smelting process occurs in a pot or reduction cell, which is a specialized container where the alumina is transformed into molten aluminum. The reduction cell consists of a steel shell lined with carbon material, acting as both the cathode and anode. The carbon lining is baked on site to produce large carbon blocks called anodes. To initiate the smelting process, alumina is injected into the reduction cell's electrolytic bath, which consists of a mixture of molten cryolite, a naturally occurring fluoride mineral, and other additives. Cryolite helps lower the melting point of alumina, making the process more energy efficient. In addition to alumina, pitch and petroleum coke are also introduced into the reduction cell. Pitch is a black, sticky substance that acts as a binder, helping to form the anodes. Petroleum coke, a byproduct of oil refining, provides the carbon necessary for the reduction reaction. Once the reduction process is underway, an electric current is passed through the anodes into the electrolytic bath, where the reduction reaction takes place. The electrical current causes a chemical reaction, separating the oxygen from the alumina in the electrolyte. The oxygen combines with the carbon anode, forming carbon dioxide, while the aluminum ions are reduced and sink to the bottom of the reduction cell as molten aluminum. The molten aluminum is periodically siphoned or tapped off from the bottom of the reduction cell and sent to the casting process. The smelting process continues continuously, with alumina continuously fed into the reduction cell, and spent anodes are regularly replaced. In Kitimat, the aluminum smelter consists of 4 buildings housing a total of 384 pots, which form a continuous line of electrical current. These pots are the heart of the smelting operation. where the reduction process takes place. Each pot is a specialized container made of steel, lined with carbon material to act as both the cathode and anode. The anodes used in the pots are crucial components of the smelting process. These anode assemblies are made from baked carbon blocks. Carbon blocks are produced on site in the carbon cell facility and undergo a baking process in a dedicated bake furnace. The anodes are baked at temperatures of up to 1,200 degrees Celsius for about 20 days. Over 600 pre-baked anodes are produced daily to ensure a continuous supply for the smelting operation. The anodes are transported to the pot rooms where they are installed in the pots. One notable aspect of the Kitimat facility is that the anodes can be changed without interrupting the ongoing reduction process. This is achieved through a well-coordinated system where spent anodes are replaced with new ones, while the smelting process continues seamlessly. This uninterrupted operation ensures a continuous production of molten aluminum, maximizing efficiency and productivity. The modernized facility in Kitimat is characterized by its high level of automation. The smelting process incorporates the latest technology and equipment to improve efficiency and productivity. Automated systems monitor and control various aspects of the operation, including the injection of alumina into the electrolytic bath, the feeding of anodes, the control of electrical current, and the tapping of molten aluminum. This automation reduces the reliance on manual labor and enhances precision and consistency in the smelting process.
The process of manufacturing a gold bar begins with melting pure gold sponge. The gold sponge, a purified form of gold, is first placed into a dedicated crucible. This crucible is designed to withstand extremely high temperatures and is used specifically for melting metals. Once the gold sponge is securely placed in the crucible, it is transferred into a gas-fired furnace. The furnace operates at temperatures ranging between 1800 and 2000 degrees Fahrenheit. This intense heat is necessary to completely melt the gold. The process typically takes about 15 minutes, depending on the amount of gold sponge being melted. During this time, the gold transforms from its solid, spongy form into a molten state, ready for pouring. Once the gold is fully molten, the crucible is carefully removed from the furnace using tongs due to its extreme heat. The molten gold is then poured into a preheated graphite mold, designed to shape it into a bar. The graphite mold ensures a smooth finish and prevents the gold from sticking during the solidification process. As the molten gold cools, it begins to harden, forming a solid gold bar. After cooling for a short period, the bar is tipped out of the mold, revealing a bright, solid, and refined piece of gold. This gold bar is now ready for further processing or direct sale at market prices. This manufacturing process ensures the highest purity and quality of the gold bar, making it suitable for various industrial, commercial, and investment purposes. Operation and setup of a gold shaker table for placer or alluvial gold mining. Gold shaker tables are widely used in placer or alluvial gold mining operations to efficiently separate gold particles from sand, gravel, and other materials. These tables operate based on gravity separation, utilizing vibration and water flow to concentrate and collect gold. Below is a detailed guide to the setup and operation of a gold shaker table, ensuring optimal performance and maximum recovery of gold. Activate the water flow system and allow water to circulate for 3 to 4 minutes to expel any air from the system. This process is essential for achieving consistent water flow and preventing air bubbles, which can disrupt gold separation. Ensure the water flow is gentle, just enough to keep the table surface wet without excessive flooding. Check the pressure gauge and regulator, setting the pressure to approximately 30 psi. While pressure is not critical, water flow must be carefully managed, as it influences material movement and separation efficiency. Verify that there are no dry spots on the table surface, as these can hinder proper material separation. Make sure the 1 and 2 cups are in place before adding material to prevent spills and losses. Begin by adding a scoop of screened material into the feed system funnel, ensuring there is sufficient water to keep the material wet. Gradually add more material, maintaining a steady flow while monitoring its distribution across the table surface. Monitor how the material separates as it moves down the table. Lighter materials, such as tan or blonde sands, will flow toward the edges, while heavier materials, including black sand and gold, will concentrate closer to the center and the cut lines. Adjust water flow to ensure gold particles enter the designated cut lines, while black sands flow past them. Increase water flow slightly if black sands are still entering the cut lines. Make incremental adjustments until only gold particles are captured. Continue this process down each cut line, adjusting water flow as needed to optimize separation. Check the distribution of materials. The table should show a clear gradient, with light sands separated from heavier black sands and gold. Ensure that the green surface of the table remains visible through the black sands to prevent material buildup and losses. After processing, collect the gold concentrate from the cut lines. If any gold particles are mixed with black sands, they can be captured in subsequent cut lines for reprocessing. Wash residual material from the table to prevent rust and contamination. Push material forward gently, without allowing it to spill into clean collection areas. Clean filters after each run, particularly when using recirculating systems. Use a pressure washer for quick cleaning of filters and hoses to ensure unobstructed water flow during the next operation. Tips for maximizing efficiency: always screen material into specific size fractions before feeding it onto the table. Common sizes include 20 mesh minus for most placer gold. Larger fractions, such as 12 to 20 mesh, run separately for better results. Screening improves separation efficiency and reduces losses. Control feed rate using the aluminum handles. Adjust in small increments, about 1/8 turn, to prevent overloading the table. Always make adjustments symmetrically on both sides of the table. Ensure even distribution of material across the table surface. If material buildup occurs, reduce the feed rate to maintain proper separation. Addressing gold losses. If gold losses are detected, screen materials into finer fractions and reduce feed rates. Test different mesh sizes and observe performance to identify optimal settings. Cleaning between runs. Remove leftover material and thoroughly clean the table and water systems to maintain performance. Use clean water to flush out grooves and collection ports to prevent clogging and contamination. The output from the gold shaker table is typically clean, smeltable placer gold with minimal impurities. For even finer cleanup, materials can be run through the table multiple times or sorted into finer mesh fractions for further processing. Adjustments to feed rates and water flow allow operators to refine separation and recover the maximum amount of gold. Refining the raw gold arrives at the Royal Canadian Mint from mines worldwide in an impure form, often containing 10% to 70% other metals such as silver. The first step in processing involves melting the gold to create a homogeneous sample for impurity analysis. Once analyzed, the gold undergoes an extensive refining process. To remove impurities, the molten gold is treated with chlorine gas, a highly dangerous procedure requiring meticulous safety precautions. Chlorine reacts with impurities, causing them to separate and rise to the surface, where they are skimmed off. This process produces gold with 99.5% purity, a level many other mints cannot match. However, the Royal Canadian Mint demands even higher purity levels. To achieve this, the gold is cast into small bars and subjected to electrolysis, a refining method employed by only a handful of mints worldwide. The gold bars are submerged in an acidic bath alongside titanium plates, and an electric current is passed through the solution. Over 2 days, gold particles migrate and coat the titanium plates, leaving behind impurities that sink to the bottom. The result is gold with an astonishing purity level of 99.99%. Once refined, the gold is prepared for minting into coins and bullion bars. The purified gold is melted and poured into molds, forming ingots that weigh approximately 50 pounds. These ingots are then rolled to the desired thickness required for coin production. Due to the malleability of gold, the rolling process must be gradual to prevent cracking. Each ingot is passed through the rolling mill 12 times, reducing its thickness by nearly 10% with each pass. Initially 11.5 inches long, the gold is stretched into strips 12 feet long and less than 3 millimeters thick. With the gold now at the correct thickness, it is punched into blanks, which are circular pieces of metal ready for stamping. The blanks proceed to the coining press, where intricate designs are struck at an enormous pressure of 133 tons. This force is more than double what is required to mint a U.S. quarter, ensuring the design's precision and detail. Each year, the Royal Canadian Mint produces fewer than 700,000 gold coins, focusing on quality rather than mass production. Its flagship product, the 1-ounce gold maple leaf, is highly sought after by collectors and investors worldwide. Valued at approximately $300, this coin exemplifies the mint's dedication to purity and artistry. The Blue Bowl Concentrator is a highly effective tool used by prospectors and miners to recover fine gold particles from concentrates. It is particularly valued for its ability to separate gold from black sand and other materials that are typically difficult to process using conventional methods. This device operates on the principle of gravity separation and centrifugal force, making it ideal for recovering even the smallest gold particles. The Blue Bowl Concentrator consists of a simple, round, bowl-shaped device with a central water inlet. It works by creating a circular water flow that generates a vortex-like effect, allowing heavier materials, such as gold, to sink to the bottom while lighter materials are flushed out. The concentrator requires a steady flow of water, which is supplied through a garden hose or pump, ensuring constant pressure and movement. To use the Blue Bowl, concentrates from panning, sluicing, or dredging are first classified to remove larger particles. The finer material is then added to the bowl. Water is introduced through the central funnel, and the flow rate is carefully adjusted to allow lighter materials to be washed away while gold settles at the bottom. Proper classification and regulation of water pressure are crucial for maximizing recovery rates. One of the main advantages of the Blue Bowl Concentrator is its efficiency in recovering fine gold particles, which are often lost using other methods. It is lightweight, portable, and easy to set up, making it ideal for both field and home use. Additionally, it operates without the need for chemicals, making it environmentally friendly. While highly effective, the Blue Bowl is best suited for small-scale operations and cleanup tasks rather than processing large volumes of material. It also requires careful setup and monitoring to achieve optimal results, as improper water flow or classification can lead to reduced recovery rates.